this section we're going to discuss periodic inspections. We go back to our Continental W670 overhaul and maintenance manual, and on page 38, section 7 is service inspection and associated maintenance. Now, this is one of those examples where things are a little sketchy. There's only a page and a half worth of information to cover daily inspections, 100-hour inspections, and major overhaul or remanufacture. So it doesn't give us just a lot of detail here, but it's still noteworthy, and we need to follow this information. Under daily inspections, it goes through 5 things that we're to be checking daily: evidence of engine throwing oil, safetying of oil plugs, carburetor and fuel lines for leakage, safety wiring on carburetor, visual inspection of the entire engine for loose nuts, screws, safety wiring, air baffles, ignition wire connections, etc., and the operation of the throttle, mixture control, and carburetor air heat control. So those are daily inspections that we need to do. The second thing it talks about is oil change. And under oil change, it says due to the different conditions, operating conditions, there may be variable time between oil changes, but they recommend oil changes every 20 to 30 hours of operation, and possibly longer if you're using an oil filter. I believe that oil filters are an excellent idea. There are at least a couple of very good options on the market today. One of those that you see often on Stearman's is the Airwolf filter, which is always on the return line back to the tank. The other filter that we're seeing more often now is the ADC filter, which is a pancake style filter and goes on the inlet side of the oil pump. Both have their pluses and minuses. The Airwolf will probably create a little bit more oil temperature in the engine. It creates a little back pressure for the oil system as it pumps through it and back into the tank, so the oil stays in the engine a little bit longer, and it picks up a little more temperature. On most Stearman's, that's not a bad thing. Because the engines are running pretty cold anyway, and we need a little more heat in the oil in order to evaporate the moisture that is a byproduct of combustion. If that doesn't get evaporated, and if you're running around at 140 degrees Fahrenheit all the time, there's going to be a lot of extra moisture in the oil. The oil will need to be changed more often, and you'll also wind up with rusty steel parts in there. So a little more oil temperature is not always a bad thing in the oil. If you're operating a Cessna 190 with a W670-23, you may have all the oil temperature you can stand already, and adding a few more degrees of oil temperature will be a bad thing. So you'll have to make a call on that. The nice thing about the ADC filter is that not only is it a very fine micron filter, it has a chip detector. So that if it finds a chip in there, it's going to let you know immediately that you have a problem in the oil filter. And also, if the oil filter ever becomes clogged and the oil filter goes into bypass, you get a light. So it tells you your oil filter just went into bypass mode, you're plugged up in the filter. And that's something that the other filters won't do. So oil filters are a great idea. I'm sure that they would have been installed originally had they been available. But as it is right now, what we on the stock Stearman engine, on the stock W670, you'll strictly have oil screens. Now we'll look at the front side of the engine for an oil change. The first thing that you'll do in an oil change is to remove the sump plug and drain the oil that's in the sump. One of the neat modifications that has been made on sump plugs is that some of the sump plugs are magnetic. And so there's actually a magnet built into the sump plug itself, so that as the oil circulates through there, anything that's steel is going to be attracted to this magnet, and as soon as you pull your sump plug, you'll see anything metallic there. And don't be surprised if there's a lot of what looks like black iron fur, because that's just the piston rings. And especially after an overhaul, you'll see a lot of that fur as the rings break in, or whenever you do a cylinder replacement with new rings. If you don't have that magnet on your sump plug, I would recommend using a magnet like this one whenever you do an oil change, and once you've got your sump plug pulled out, just push that magnet down in the sump and let it, feel around for anything that is ferrous. If you have a rear main bearing that is beginning to fail, the parts will wind up falling down into the sump, and you'll pick them up with the magnet. So if you don't have the magnetic sump plug, use a magnet and feel around down in there anytime you do an oil change. Now on the back side of the engine, you basically have two locations that will need to drain oil from. One is the high pressure oil screen, so you have to cut the safety wire here, thread the high pressure oil screen out, and inspect it for metal or gasket material or anything that might be gathering there. It's also a good idea to use the magnet on the high pressure oil screen housing too, because if there's anything that is laying in the bottom of the housing, you'll find that with a magnet, and this is a fairly fine screen. The one other location is the scavenge oil screen, which is right down here, just above the step-up drive, kind of between the step-up drive and the left magneto. Now that one often gets ignored because it's kind of buried in there behind everything and deep into the accessory case. But again, if you're having a main bearing, a ball main bearing failure, parts of the main bearings will be collected there in that scavenge screen. So it's always worthwhile to pull that screen out as well and check it for any debris. Now the only other place that you'll have to drain oil from will be draining the tank, and most people on a Stearman will have a Y drain to drain that. If you have a Waco or a Fairchild or some other aircraft, you may have a different oil drain system. But on the engine itself, there are these three locations: in the sump, the high pressure oil screen, and the scavenge oil screen. The next operation that we have in our service inspection and associated maintenance is, under 100-hour inspection, the magnetos. And before we go back to the back side of the engine and work on the magnetos, we want to set it up so that we can check the magneto timing accurately. And in order to do that, we're going to use a time right, but we're not going to use the time right in the way that it normally is used. If you use a time right and the time right card, you can get the timing pretty close. You can get within a degree or two, which is close, but we found that using a crankshaft protractor and a pointer, we can regularly get down to about half a degree. So we can get a lot closer with our magneto timing than with just a time right. Time right's okay. This is better. And so we're going to set up the protractor on the crankshaft and go through checking the timing on the magnetos. All right, we have our pointer and our disc installed now. The reason that I said that the time right is not as accurate, let me show you what happens here. As we move towards top dead center, as the piston is reaching the top of its travel, then the piston reverses itself. And in that process of rising and then reaching top dead center and reversing, all the slack of all the clearances in the engine suddenly reverse direction, so that whereas it was pushing, now it's pulling. And there's a certain amount of time when not much is happening right around top dead center. So we can watch our little pointer here, and our pointer is coming up towards top dead center, reaching top dead center, it's moving. Now it's stopped moving. It's continuing to go nowhere for several degrees until it begins to move again. Now, as it reaches top dead center, there's a point at which because everything is reversing direction there, there's a certain amount of slop. Well, the time right is fairly inaccurate at that point. It has a hard time determining exactly where top dead center is. Is top dead center here? Is it here? Where exactly is top dead center? Well, if we don't know where top dead center is exactly, then we don't know where 29 and 32 are, which is where we're supposed to be timing our magnetos. So what we want to do is we want to use the time right to help us find top dead center. And then once we've found top dead center, then we're going to ignore the time right and we're going to do it all with the protractor. Now, you might say, well, I don't want to take my propeller off every time I check timing. Understandable. There's also this little device, the universal true timing indicator, which just clips over your propeller with bungees, and this thing will serve the same purpose as the timing disc and the pointer. So you don't have to pull the propeller in order to do this very accurately. All right, the first thing that we're going to do is we're going to estimate where top dead center is. We're going to say, yeah, it's not moving much there, so that's probably pretty close to top dead center. And now we're going to set our timing disc at 0. So we've got our timing disc is graduated 0 to 90 and then back again to 90. And so we're going to set to 0 and we're going to tighten this thing down. All right, so we're marked at 0 there. Pretty inaccurate, but it'll be close to start with. Now, you'll notice that I have a piece of green tape on here. That's really what we're going to use to check our timing. So what I'm going to do is I'm going to move this till the indicator goes all the way to the top. Now I'm going to bring it back until that pointer is even with the top of my piece of tape. Okay, it's even with the top of the piece. Now I'm going to read what it says here. And it says 25 degrees before top dead center. Now I'm going to go to the other side. It goes down past top dead center, comes back up again. Now I'm going to take the slack out and I'm going to check it on the other side. And on this side, when the tape is even with the top of the pointer, it says 34 degrees before top dead center. So one side is saying 25, the other side is saying 34. Okay, that's a 9-degree difference. So what that tells me is that, not that I'm off by 9 degrees, I'm off by 4.5 degrees. So what I need to do is I either need to add 4.5 degrees to 25, or need to subtract 4.5 degrees from 34. Both will give me 29.5 degrees. So I need to loosen my pointer, or loosen my disc, and move this to 29.5 degrees. Okay, now I'm going to check it on the other side again. Let's go to the other side. Okay, we've gone past it. Now we're going to come back. The pointer is now even with the green, and it says 29.5. I can go to this side, go past, check it again. I'm right there. It says 29.5. What that tells me is that when I go to 0 and check it, that truly is 0. I've taken all the slack out of the system. I've checked it on both sides, and I removed all the play from the system. So now, when my pointer reads 0, it truly is at top dead center. All the slack has been taken out of the system. Now I can with confidence, I can ignore this now. I can come over here and say, we're going to check the left magneto. Left magneto, according to the book, is supposed to be at 29 degrees before top dead center. So I can bring this to 29 degrees before top dead center, and I can be confident that that truly is 29 degrees before top dead center. Now, the other thing that we need to do is we need to be sure that we're 29 degrees before top dead center on the compression stroke. So we'll take our time right out. And we're going to put our thumb over the spark plug hole, and we're going to check for compression. Okay, coming up on top dead center, I don't feel any compression. Okay, so let's bring it back around again. There's the compression, and if I go past 0, then it begins to push. It begins to pull on my thumb. Okay, so we know that that's the compression stroke. Now we can go back here to 29. .29 before top dead center. We're ready to set the left magneto now. All right, now we're back around on the rear of the engine, and you'll remember that we're working on a W670 6A engine, so we have the VMN7 DF magnetos on it, and the overhaul manual gives us some detailed directions on page 80 and 81 about timing the magnetos, and it tells us that the right magneto is supposed to be timed at 32 degrees before top dead center, and the left magneto is supposed to be timed at 29 degrees before top dead center. And that's the same whether we're talking about the W670 6A with the VMN series or the SF7 RN1s on the W670-6N. Now the reason that they stagger the timing like that at 29 and 32 is because the right magneto is firing the front spark plugs and the left magneto is firing the rear spark plugs. Now what we know, because of the cooling air that is hitting the front of the cylinder is much cooler than the rear of the cylinder is. So what they do is they start the combustion event with the right magneto at 32 degrees before top dead center, and so the flame begins there and starts moving towards the center of the piston, but it's moving slower because it's colder. The rear one, they give it another 3 degrees before they start the combustion event and fire that spark plug. That way the flame front meets the center of the piston at the same time, in theory. Now this is probably a good time to talk about a little data discrepancy that we have between the overhaul manual and some other Teledyne Continental literature. We talked about on page 80 and 81 it giving us the 29 and 32 degree number. There was a mandatory service bulletin, MSB 94-8C, that tells us different timing on this engine. And so if we go to the back page of that service bulletin, it tells us that both the right and left magnetos are supposed to be timed at 32. So that agrees with the timing in the book for the right magneto. It disagrees with the timing on the left magneto. So what I did is I contacted Teledyne Continental, and I also contacted our local FSDO about it. And what the FSDO said was, what does the type certificate data sheet say? So we looked up the type certificate data sheet, which agrees with the overhaul manual, but disagrees with this mandatory service bulletin. The FSDO said, as far as we're concerned, the type certificate data sheet is law. So if it says 29 and 32 on the type certificate data sheet, until that is amended, that's the number that you need to go with. When I contacted Teledyne Continental and pointed out that their mandatory service bulletin did not agree with the type certificate data sheet, they said, whoops, we're going to have to do something about that. And so that may be amended in the near future, but at this point there's a disagreement between a mandatory service bulletin, which is FAA approved, and the type certificate data sheet, which as far as the FAA is concerned is law. So until I hear differently, we'll be timing them the way that they always have at 29 and 32. Now what we want to do is we want to look at these magnetos, and we'll get in close so that you can see internally what happens with these magnetos as we're timing them. All right, here's our left magneto. Now, in order for us to time this magneto correctly to the engine, there are three conditions that will have to be met. The first of those is that the points will have to be adjusted to 12 thousandths. Then there are some hash marks that have to line up on the magneto, and the engine has to be at 29 degrees before top dead center for the left side. Now we're going to remove the point cover. In order to do that, there's a piece of safety wire that I've already cut here that goes from the P-lead tower down to the arm. So now we can rotate the arm out of the way. We can throw this little lever out of the way, and the point cover will come off. Now we're also going to take the coil cover off, which is held on by two screws, just so that you can see things a little easier than if the coil cover was left on. Now if you look closely, you can see the little hash marks. There are marks on the magneto housing, and there is a mark on the big gear here. There are two marks on the magneto housing here and two marks on the big gear. Those marks all have to line up, and the points have to just be opening when they've been adjusted to 12 thousandths, and the engine has to be at 29 degrees before top dead center on the compression stroke in order for this magneto to be timed in correctly. But the first operation is always to make sure the points are adjusted correctly. If you set the magneto timing and then adjust the points, adjusting the points will throw the timing off somewhat. So if you can look very carefully here, you can see that the points are closed right now. And what we're going to do is rotate the crankshaft until the cam in the magneto, the cam follower on the points is on the top of the lobe of one of the lobes on the cam. And at that point, you can see the points opening now, and that's about their widest point right there. This is a handy dandy little tool. It's a Bendix Scintilla wrench that has a 12 thousandths feeler gauge on one end and a 1/4 inch box end wrench or open end wrench on the other, which allows us to adjust the points. We're going to check these, and so we put our feeler gauge in there, and that is just about right. There's just a slight drag on the feeler gauge as it goes between the points. Now if the points had needed to be opened or closed, we would take our wrench, which you don't have to use this special little wrench, you could use any small 1/4 inch ignition wrench, loosen this lock nut, and then move the point either in or out until you got a 12 thousandths clearance there. Okay, so first off we want to set it to 12 thousandths, and then at 12 thousandths, once we have that, then we're going to set the crankshaft back to 29 degrees before top dead center here, 32 degrees before top dead center over on the other side, and then we will time the magneto to the engine. Okay, so now we have our points adjusted to 12 thousandths. We've got the crankshaft set to 29 degrees before top dead center on the compression stroke. And now we're going to time the magneto to the engine. I've loosened all three of the magneto adjustment bolts so that we can take the magneto and rotate it through its full range of motion in order to time it. I've got a magneto timing light set up here. So what we're going to do is turn the timing light on, and we're going to look for the place where the points just open. All right, that's the place where the points are just opening. So now we'll tighten that up. We'll go around to the front of the engine, and we'll back up the crankshaft to about 50 degrees before top dead center. We'll turn our light back on, and now we're going to bring it back to 29. There we are, 29 degrees before top dead center. We just completed timing the left magneto on the engine. Okay, here's our SS7RN1 magneto, and we're going to time this one on the bench since we have a W670-6A engine out there and this won't fit it. The SS7RN1 is similar to the VMN series but has some pretty important differences. The points are under the point cover, which is on the very rear of the magneto. You have the points in here and the condenser. The coil cover is held in place by these two straps, which once we take the straps off, the coil cover comes off and the coil is exposed. Now, one of the similarities is that the SF7RN1 also has hash marks both on the rotor and on the housing, which I have again highlighted with black magic marker so that you can see them better. They're usually just a scratch and pretty tough to see unless you're really looking for them. And you can see that they move with relationship to each other. Now, one of the major differences with the SF7RN1 is that you only have two conditions that have to be met at the same time, which is the points have to be opening and the cam is cut in such a way here that it has a step. And there are some little marks, and you can see that I've highlighted that with the magic marker, and little marks on either side. And with that step in the cam and those little marks, what we have to do is take a straight edge and lay it across there. And laying the straight edge across, these marks have to line up with the cam at exactly the same time as the points are opening. But this mark, unlike with the VMN series, this mark can be approximate. If it just generally points in the right direction, that's okay. These are critical. These have to be happening at exactly the same time. These can just be happening approximately. So what we're going to do is go ahead and hook up the timing light to it, and we'll check the internal timing of this cam to see, or this magneto, see how it's timed. Okay, so we'll lay our straight edge across here, and we'll look for the opening of the points. Okay, the points are opening right there. You can see that here's the mark. It's about 3/8 of an inch off. So the points are pretty badly out of adjustment on this one. We need to adjust the points not to any specific value. So whereas with the SF7 or the VMNs we were adjusting them to 12 thousandths, on the SF7s there's no particular value that we're adjusting them to. We just adjust them until they open when the marks on the point plate are lined up with the cam. And we have two screws here that hold down our points, and we have one eccentric. So when we loosen these screws, we can turn the eccentric and it'll open or close the points. So what we're going to do is we're going to go ahead and line up our marks. Okay, so we've got our marks on both sides lined up with the cam. Now, without moving the magneto at all, we're going to loosen our points. We'll turn the timing light on, and we'll adjust the points with the eccentric until they are just opening. That's it right there. Okay, we'll tighten these down again, and then we'll double check it with the straight edge and make sure that nothing moved. Okay, so yep, points are just opening as we hit the marks on the housing here. So now this is timed and it's ready to time into the engine. All we have to do is set the engine up again at 29 and 32, plug the magneto into it, and then check it again so that to verify and rotate it through its slots until the points are just opening at 29 and 32, and we've got the internal timing of the mag all taken care of. There are probably a couple of other things that we should say about the VMN series magnetos before we go on. The first is that when we're timing this, we need to be sure that this advance lever is all the way in the full clockwise as viewed from the rear, which means the full advance position. If we time the magneto back here, it will actually be retarded and it won't be timed correctly. So we have to time it in the full advance position, and then once you're finished doing anything with the points, safety it off against the P-lead tower here. The second thing is that originally these magnetos came out with some oil cups. Little oil cup back here next to the base of the magneto, and little oil cup out here on the coil cover. The instructions in the service manual for the VMN series magneto is that they get 25 drops of oil every 25 hours. 40 weight oil works well, 50 weight oil. But what they found after a few years of operation was that this coil cover cup was oiling the rear ball bearing on the rotating magnet, and it was washing out that bearing, and the bearings were burning up. So what they decided was that rather than oil this, they would grease it at overhaul and then never oil it again. So in 1957, there was a service bulletin that came out, service bulletin number 327, that said, do away with this oil cup, and so they instructed that it be soldered closed. Now this oil cup, which actually oils two different places, it oils the front rotating magnet bearing, which is also a ball bearing, and it oils the rotating cylinder. Now the rotating cylinder axle is just a plain bronze bushing running on a steel axle, so it's very, very important that one get oil, but they didn't want oil getting down here. So what they did is they instructed how to push a wire down inside of here and block off one passage while leaving the other passage open, and they instructed that we go in and use a mill to mill out that other passageway so that it got more oil. So it's very, very important that this rotating cylinder axle get oil. If it isn't oiled, and you just trust the assembly grease to lubricate that, that will last for maybe a couple hundred hours, but sooner or later that plain bronze bushing is going to get hot and fail. If you're fortunate, what will happen is your rotating cylinder will just break. We saw one of those happen last week, break from lack of lubrication, and that mag will stop working and you'll realize that you've got a problem there. We've seen them where it got so hot in there because of lack of lubrication that the rotating cylinder, which is made of phenolic, began to actually flow and melt. One instance, which was a pretty radical one, it burst into flames and actually caught fire. So it's very, very important that that be oiled. What you probably should do is look at your coil cover cup, and if that oil cup is not soldered closed, then your service bulletin probably has not been complied with and needs to be done. Important service bulletin that you really don't want to let slide. Now another thing, not just with the VMN series magneto, but also with the SF7s, is the rotating magnets are not a natural magnet. They're actually an artificial magnet that was magnetized when the magneto was assembled at the factory. They need to be remagnetized from time to time. They will bleed out their magnetism over a period of years, and with the result that the spark will no longer be very hot. Now the problem is that a lot of overhaul shops didn't have magnet rechargers, so they would overhaul the magneto but not recharge the magnet, and you'd have a magneto that was coming directly out of overhaul that was throwing out a pretty weak spark. So at least at overhaul of the engine and the magneto, the rotating magnet needs to be recharged, and it'll make the difference between night and day on starting with these things. The coming in speed will drop dramatically so that you just barely have to rotate the magneto, and it's throwing sparks all over the place with a nice hot magnet. So very important that the magneto's rotating magnets be recharged from time to time. Now one other type of ignition that you may come across on a W670 is the WL7A battery distributor. Originally, many of these engines were equipped with either one or two WL7A distributors, so that some of the engines came out without magnetos at all. They were equipped with two distributors, some with just one distributor, but this was a very common thing with the early engines. This is basically just your 1956 Chevy distributor with points and condenser and rotor and flyweights, so it's a mechanical advance distributor. About the only place you see them today is on the W670-23 engines, the ones for the Cessna 190s. And what you'll see is the WL7A over in place of a right-hand magneto. And then on the left-hand side, you'll see the VMN7DFA magneto, which is an automatic advance mechanism in it. So both of these have automatic advances. Both of them will be starting retarded, which will give you a really easy start. And then their advance curve advances the spark up, so that at rated RPM, then you're running at 29 and 32, just like the ones that are fixed advanced. Now this is one of those other places where we have a data conflict. If you go to the W670 overhaul manual, it says that on the W670-23 engine that the battery distributor should be timed in at 5 degrees before top dead center, and then it advances up to 32. And they say that the automatic advance magneto should be timed in at 17 degrees before top dead center, and then it advances up to 29. Don't have a problem, that works well. If you go to that mandatory service bulletin that came out in 2007, it agrees with 5 degrees on the battery distributor side, but on the magneto side, they actually have you retarded a little bit and set it at 14. So 3 degrees retarded from where the overhaul manual. That will still work well. That's not a problem. The problem that we have is with the type certificate data sheet, which is that piece of paper that we talked about a little while ago that is law as far as the FAA is concerned. What the type certificate data sheet says for the W670-23 is that we're supposed to set it up the same way as we did the 6A and the 6N. So we're supposed to set it up at 29 and 32. Now what will happen if you do that is that it will start fine, because it's starting about where it should be running. But as the RPMs come up, you're going to advance way out into a detonation place. It's going to start running terrible, because you're going to be advancing up to 55 or 60 degrees before top dead center, and that's a really dangerous thing. I contacted the FAA's Atlanta Aircraft Certification Office, which is the responsible office for the type certificate data sheet for the W670 engine. They looked that over and they said, "Oh, well, we got a problem here. That's really an unsafe condition." And so I expect to see that changed with a revision to that type certificate data sheet E162 in the next little while. But you just need to be forewarned that what is on the TC data sheet right now is incorrect and is unsafe. All right, let's come back to page 39 in our overhaul manual, and we'll finish up this periodic inspection. The next thing in the list is the valve adjustment, and what we're going to do is walk through a valve adjustment here. We'll again need to find top dead center on the compression stroke, and so we'll start with number 1. We'll bring it around. Nope, that wasn't the compression stroke. No compression coming out. Bring it around. All right, and it's not important that it be exactly at top dead center. If it's within a few degrees, and we know that our bar is pointing to the number 1 piston at top dead center, so that's close enough. Now what we're going to do is we're going to check both the exhaust and intake rocker arm for clearance between the roller and the tip of the valve stem, and we're looking for 10 thousandths of clearance there. So we'll check that. If it's not at 10 thousandths, we need to loosen that adjusting lock nut, move the adjustment screw until we can get a 12 or a 10 thousandths feeler gauge, drag it through there with a little bit of resistance, and then relock the lock nut securely, and then we'll move on to the next cylinder, which in the firing order is 1, then 3, so we'll come down here to number 3. And again, we'll check for compression, though we have to have it. This is the firing order. So there it is. We've got compression, and we'll do the same thing here. We'll adjust the number 3 to 10 thousandths if they aren't at 10 thousandths, and then we'll go to the next one in the firing order, which will be number 5. Then we'll come up here to number 7. Then we'll come to number 2. Then we'll do number 4. Then we'll do number 6. And then we come back to 1 again. That's the next one in the firing order. Now, we've just checked all of the valve clearances for the first lobe of the cam. Now let me show you what I'm talking about here. This is a W670 cam, and you'll notice that the cam has 3 lobes on the exhaust track and 3 lobes on the intake track. So this is a 3-lobe cam. Now what we've done is we just checked the valve adjustment on 1 of these lobes, but we don't know about the other lobes. We don't know if there's variations in the lobes that are going to create a problem with the other as they open the valves. So what we have to do is we have to go back through this process 2 more times. Now what that's going to mean is a total of 6 revolutions of the engine. The first 2 will be checking the first lobe, the next 2 will be checking the second lobe, and the last 2 will be checking the third lobe. Now as we go through the other 3 or the other 2 lobes of the cam, what we'll be looking for is to find that nothing is tighter than 10 thousandths. So what if now that we're back on number 1 on the second lobe of the cam, we find that the exhaust is at 10, but the intake is at 11? Do we want to adjust the 11 back down to 10 again? No, because what that means is that on that first lobe, it'll now be 9, because we're tightening it up. So what we want to do is just make sure on the second and third lobes that nothing is tighter than 10. The engine will run fine a little bit loose. It won't run fine a little bit tight. If the valves get tight, then they'll hold the valve open and you'll wind up with a burned valve. If the valves run a little bit loose, the worst thing that'll happen is the roller will hammer a little bit on the tip. And I'm not talking about a lot loose. If they're a lot loose, it'll actually mushroom the tip of the valve over and hurt the roller. But we're just talking about a couple or 3 thousandths here. If you have a lot of variation, you may have a problem with your cam. But normally we just see 2 or 3 thousandths of variation. So make sure on that second and third check, which is actually number well, you've gone around once, twice, now you've checked 1 lobe, now 3, 4 times you've checked the second lobe, 5 and 6 you've checked the third lobe. On the 3rd, 4th, 5th, and 6th times around, make sure that nothing is tighter than 10 thousandths. And once you've got all that, double check all of your adjuster nuts to make sure that they're locked, put the rocker covers back on again, and the periodic inspection is over.